Thank you very much. It is very much a pleasure to be back in Mallorca. I've had a number of trips here now, thanks to hosting by Joaquin and Ananda. And when Jacques mentioned a couple of years ago that there was going to be another GODAE summer school and it was going to be in Mallorca, I was like, there, count me in. So I'm here the whole 2 weeks to prove that I really do love this place. So I'm available for ROMS consulting anytime until next Saturday. I know some of you are ROMS users, so you may know that Rutgers University is the home of myroms.org. We run the bulletin board and the wiki. I know it's not very complete, and try to do our best to help the ROMS user community. So I'm an ocean engineer. I'm kind of a practical fluid dynamicist. So what I want to go through in this lecture today is explain just all the steps that we went through to set up a near real-time operational coastal forecast system. And in my second lecture, beginning of next week, I'll carry through this model configuration that we've set up and talk about what we're doing with real-time data assimilation and observation impact analysis, sort of thing that Meninya talked about briefly this morning. Okay, so everything I'm doing is really the work of all the other people, and I just get to stand up here and have 2 weeks in Mallorca. But before we get started, a little motivational talk. If you haven't heard this drumbeat of societal impacts yet in your career, it will come to you. And I've just taken some resources here off the the American IUS Integrated Ocean Observing System webpage, and they classify their main themes as safety, the marine economy, and the marine environment. So operationally, there's some very important immediate benefits to having good ocean state estimates and forecasts, and that's if you fall overboard when you're on the ship this Friday, you hope that Coast Guard will know where to look for you. And so if there's a good ocean forecast from SOCIB, they should be there right away to pluck you out of the water. So nothing to worry about. Storm surge I will return to at the very end of the talk. Oil spill tracking is another. If you look at the numbers for the US economy, 2.8 million jobs in the maritime sector. It's a big part of the economy. And issues to do with sustainability, harmful algal blooms, all of these different things are all reasons that products that analyze and predict conditions in the coastal ocean are economically important. And a recent one is recent deployment off the coast of Washington, where now we're seeing the effects of low oxygen waters and low pH waters actually directly impacting the contemporary shellfish industry. And the shellfish industry, through their lobbying of Congress, got NOAA to put in some extra buoys along that coast to monitor those conditions. So these are all reasons that we care about the coastal ocean. So just kind of a thought experiment. So to explain why it's a challenge. So the continental shelf sits between the terrestrial runoff from land and the deep ocean, which we have all of these observations from the global observing system, from global and basin scale GODAE-class data assimilating models. And if you want to get conditions in the coastal ocean correct, say you just want to get the across-shelf gradient in salinity from 0 at the river through the estuaries to 33 or 35 parts per thousand at the shelf, then you have to be able to observe and model those across-shelf fluxes at the shelf edge. And that's a very challenging problem because of the steep bathymetry, very short length scales within shelf dynamics. And so, and this was a point that was posed to me by Steve Lentz at Woods Hole Oceanographic, and he said, well, if your model can't get the across-shelf gradient in salt, where you've got all of these observations of salinity, how could you possibly think that you would be able to estimate or observe the across-shelf fluxes of nutrients that are feeding that ecosystem, cross-shelf export of carbon that's fixed there into the deep ocean and burial? So we need to be able to get the physical circulation right before we start the sort of biogeochemical processes. So what I say about coastal ocean forecast systems is that when they're operated as nowcast or forecast systems, and they have high resolution, and you're downscaling a good estimate of the ocean state at the open boundary from a global model, like a GODAE model, then, and you add in the extra dynamics that are important in coastal ocean, and you've got good quality forcing from your meteorological model because you've got land and mountains, varying things, and you've got a data assimilation scheme, and you think about interdisciplinary processes, then you can produce actionable guidance. So information that's a product that someone can actually use to make an informed decision about the ocean, and that would relate to water quality, public health, shipping, search and rescue, and all those things. So that's what we're trying to do. We want to build a model that does that. So this is my region of interest, northeast United States, and all the way up to Canada. And the circulation here has some similarities actually to the circulation in the Balearic Sea. We've got a boundary current that's trapped along the shelf that heads towards the southern end here, separates from the coast and detaches. In our region, that separated shelf flow actually joins the Gulf Stream. And so we've got relatively low salinity water coming in at the north from the Scotian Shelf, Labrador Sea, very high salinity water coming in from the south through the Gulf Stream, an energetic Gulf Stream that exits through one of our open boundaries, and mesoscale variability in between. So this is the modeling domain we've set up, and this is where we want to take boundary conditions around here from GODAE, configure this model as well as we possibly can in terms of forcing and resolution, and then have the downscaled solution in that area on which to base our products that would give actionable guidance to people in the maritime sector. Okay, it's a relatively well-observed region. IUS is organised by regional associations. Rutgers University is a member of MARICUS, the Mid-Atlantic. Schematically here you see velocity vectors from our HF radar network, the trajectory of a glider, various stations along the coast, some satellite imagery. In the Gulf of Maine, there's a NERICUS, Northeast Regional Observing. They tend to have fixed assets, current meter moorings, fixed buoys that are measuring biogeochemical properties. And right in the middle of this, the National Science Foundation has recently deployed, or in the last 2-3 years, the OOI Pioneer Coastal Array, which is 7 fixed moorings with profiling CTDs, a fleet of gliders. There's usually 2 or 3, sometimes 4, patrolling this area. 2 meteorological moorings with a full package that measure fluxes through the boundary layer. So that's a really dense array of observing systems right in the middle of MARICUS. So that's great. And a very dynamic gradient across the shelf. When a warm core ring from the Gulf Stream impinges on that shelf, the eddy fluxes are very intense and the scales are small. So, ROMs. Hydrostatic primitive equations, nothing exotic, just a good old 3D circulation model. A couple of features, I shouldn't dwell on these. ROMS has, I feel, a very sophisticated suite of numerical algorithms under the hood that make it run. It's in terrain following coordinates, which is a significant advantage in coastal shelf modeling, because there are a lot of issues to do with topographic control and a smoothly varying or continuously varying bathymetry helps with that. The vertical coordinate system in ROMS allows quite a bit of flexibility in the stretching so that you can resolve well the surface boundary layer and the bottom boundary layer, and those boundary layer processes are important in the coastal ocean. I won't go through any of the numerics. I would send you to this 2009 paper of Shepetkin and McWilliams. It's quite encyclopedic. It's difficult to get. I could accidentally leave a thumb drive here with a PDF on it that you could download if you're interested. And it's a structured grid. Move on from that. It has a very flexible turbulence closure scheme in it, this GLS scheme that of Umlauf and Boycard that John Warner implemented. And it means you can use a K epsilon closure or a K omega or the Mallory-Yamada KKL scheme or McWilliams KPP, and you can actually just switch them off and on and see if it makes any difference. It doesn't make a lot of difference, but you do have to have a good closure scheme if you want to get some of these boundary layer processes correct. So I won't dwell on that either. We have a two-way nesting capability in ROMs, and we do it the same way that the parallelization is done, where the domain is cut up into small tiles, and there's an overlapping region of 2 or 3 grid points that you need to complete the numerical stencil on each. So in the nesting, we just say, well, you know, this inner grid here needs to have some information 2 to 3 grid points outside in order to complete the 3rd or 4th order advection stencil. So we just interpolate those from the parent, and then the child model does its 3 time steps, if it's a factor of 3 refinement, for example. And then the parent grid out here just gets replaced with the child grid inside, and off it goes. And so this exchange is done exactly the way the parallel coding is done in ROMs. So it's done on every iteration, every time step. It's done in the predictor and the corrector. It's actually done at several places in the code wherever there is any communication required. So it makes it rather complicated, but it makes it rather precise. So that works well for us now. And as an example, so for our work with the NSF Pioneer Array, so what I'm showing here is the moorings and the white triangles. The colored lines are the nominal glider tracks. Now, they never actually go in straight lines like that, but they're doing the best they can. So we have a nest here that's within the larger domain, and then we have another nest inside this that's right here. So we go from a 7-kilometer grid to a 2.5-kilometer grid to a 700-meter grid, and these nesting exchanges are two-way at every level. So the parent grid takes 1 time step, this nest takes 1, 2, 3, and then this takes 1, and then it goes back and forth, and it takes a long time. So, as resolution increases with nesting, for example, more physics becomes explicitly resolved, and we've seen some very nice examples from Baylor in his talks the last 2 days about what happens when you put finer and finer resolution in. You get more and more variability, and you actually get to resolve different physical regimes. So the things that, other things that become important in the coastal zone are things like wave radiation stress set up against the coast, wave current interactions that modify the bed stress. So you might want to couple your circulation model with a wave model. So that's one of the things that we do in ROMs. You may need parameterizations for wave breaking because that affects turbulent kinetic energy in the turbulence closure model. Storm surge. It comes up, covers the land. Some of your grid cells that were wet were dry, become wet, so we resolve that as well. And there's other reasons to couple models with atmospheric circulation models or sea ice models. And something that's new the last couple of months in our version of ROMs is that we've implemented the ESMF new op-sea coupling. And so there are a lot of models out there, the Los Alamos sea ice model, regional climate models, WaveWatch 3, WAM. They all have an interface through this new op-sea. So now we're at the point where if you have some familiarity with that nesting paradigm, coupling paradigm, you can start using ROMs with that. So we have feedbacks between ecosystems and sediment transport in ROMs. So some of those added physical options are actually described in this paper about another version of ROMs, Coast, which from time to time realigns with our version that we have at myroms.org. Lots more physics. More physics is always better, but you need to have the resolution to resolve it. We have sediment transport models that can move bed load, suspend sediment into the water column. We've done some work where we allow that suspended sediment to actually affect the light attenuation along with chlorophyll in an ecosystem model. And in certain estuary environments, that becomes important. So here's sort of an idealized example. For a 2-dimensional estuary, it's somewhat like the Delaware Bay, if you know the region. So the black lines here are salinity. So there is a turbidity maximum here with suspended sediment. This is chlorophyll distribution. and this is nitrate. Plenty of nitrate coming in the Delaware River and out of the city of Philadelphia sewage treatment, but we don't get a chlorophyll here, we don't get a physical bloom because the suspended sediment suppresses the light. And if you carry this through and look at the average primary productivity, if you have the sediment light attenuation, the productivity is limited to the surface because of the shallow optical depth, and there's nothing in the upper reaches of the river. But if you don't have that attenuation of light due to the presence of inorganic sediment, you have a bloom all the way across as soon as that water comes in. So these things, these are important factors if you're trying to carry through to water quality in an estuarine environment. So this would be actionable guidance for someone that's trying to decide, should we put a lot of effort into reducing the nitrate load in the Delaware River? You could say, well, maybe not, because there isn't enough light to ever give you a nuisance algal bloom. Whereas in the Chesapeake Bay, it's absolutely a problem. So, okay, so now we're going to build this model. I'm going to have to speed up here. So this is the domain we're calling, and we refer to this model as DOPIO. There's some history to this. We used to have our old prototype model was a small thing here we called Espresso for experimental system for predicting shelf and slope optics, and the new domain is about twice as big, so it's a double espresso. DOPIO. People keep asking me, what does DOPIO stand for? Okay. So what do? We've got open boundary data that we take from, in our current real-time version, the Mercator 7-day forecast from Copernicus. We add harmonic ties to that, and I'm going to say some more about pre-processing of those data. We take the National Weather Service 72-hour forecast, NAM, the model, and we have river sources here at the little green triangles. We get gauge data from Geological Survey and Environment Canada, and we have scaled that up with a statistical model based on a very high resolution, a 5-kilometer resolution watershed and surface water flow model. Because the gauges are a little bit upstream, and there's a significant portion of the watershed that they do not measure. And if you don't make that adjustment, you significantly underestimate the amount of buoyancy that's coming into the system, and you'll have too much salt in your ocean, and you won't get Steve Lentz's salt balance correct. Okay, we find as good as Mercator is, and we've definitely charted the improvement in Mercator over the last decade, it still has some biases when we compare it to our very high resolution regional climatology, MOCA. If you see the trend evolving. So this is what the bottom temperature annual cycle looks like in the Mid-Atlantic Bight. It's actually warm-ish at the bottom in December and January, and the coldest months are February, March. And then walk off the edge here. The shelf stratifies from the south and moves northward. I'm going to skip over this little movie and just show here. So this is a cross-section along the 65-meter isobath, and I've started in March, the coldest month. And then you can see around about May, the warming begins in the south, and you get a shallow thermocline there, and it progresses northward quite quickly, and it cuts off water that's cooler than 9 degrees here, and we get left with this sort of blob of cool water at the bottom, cold pool. So bottom temperatures in the middle of summer of less than 9 degrees Celsius, surface temperatures around 23 in 65 meters of water. Sea surface temperature from satellite is not going to tell you anything about those bottom temperatures. So getting actionable guidance about bottom temperatures is critical to managing fisheries in this region, because we have a large scallop and surf clam fishery. So this is information we need to have. So what do we do? We take this climatological data and all of the long-term observations, mean observations of ocean circulation. So the Oleander is a container vessel that goes to Bermuda every month. It's got an ADCP on board that's been running for 20 years. We have a very good estimate of the mean current here. There's some long-term current meter deployments in the blue arrows. This is a 5-year mean of surface currents from our CODAE network. If you go into the Gulf of Maine, there's been an extensive surface drifter program there that gives mean velocities. And we actually take all of these estimates of the mean state of the Mid-Atlantic Bight, hydrographic climatology, velocities, and surface forcing, and we put that through our data assimilation system that we've configured in a way to give us a mean estimate. I won't go into the details of that, but what it ends up giving us is a three-dimensional annual mean temperature, salinity, velocity, and sea level that satisfies the ROM's physics, so governing equations, flows along isobaths, is steered by the bathymetry as it is, which would be a very challenging thing to calculate just from a hydrographic atlas itself. And that gives us mean sea surface, so mean dynamic topography. So now you can see a very strong gradient across the shelf that drives this mean flow towards the south. Here, this is the Gulf Stream hauling through this. We see boundary currents in the Gulf of Maine, and qualitatively you can see the sense to this general circulation pattern in the mean dynamic topography. This now is a mean sea level to which we can add anomaly sea level from altimetry, and we use coastal altimetry all the way into the 20-meter isobath. It also means that we can correct our boundary conditions. So what we do is we've taken a long-term mean of the Mercator analysis in this area. We subtract that mean out and we replace it with our dynamically adjusted, through data assimilation, climatological estimate, so that we are removing long-term biases in Mercator. Mostly they stem from the salinity in the Labrador Sea being too high, and if you don't have the right salinity coming in up here, of course it flows through the whole system, and you are constantly assimilating observations that are at odds with what is at the boundary, so you really want to correct those boundary biases. You can also learn some things about the oceanography just from having done that modeling and data assimilation calculation of the mean circulation. So here is this, the view I just showed you of temperature along the 65-meter isobath in the annual mean. And I now have a velocity solution that corresponds to this. And this is the across-shelf velocity. So where it's red, it's coming out of the page toward you, and where it's blue, it's going into the page. So in the the black line is the average over the entire mid-Atlantic bight. And then you'll see something that agrees with a very nice analysis by Steve Lentz that there's an inflow through most of the water column, but there's offshore flow in the surface Ekman layer because the winds here are easterly, and that's Sediment Transport. And since there's a long shelf flow, there's a boundary layer at the bottom, an Ekman boundary layer at the bottom. And you have a process like this. Offshore flow here, offshore flow at the bottom. This is the sense of the wind into the page. And so in a two-dimensional sense, you kind of have to conserve mass by having some flow coming in the center. That has to be geostrophically balanced, so that tells you that there's a long shelf pressure gradient to sustain that across shelf geostrophic flow. And we can see that in that mean dynamic topography. Okay, so now we've corrected our Mercator open boundary information. We apply those at the perimeter. We use a combination of active-passive. This is the Marchesiello scheme, nudging. We have some flow relaxation in a nudging zone here, which was the importance of which was something I learned at the first summer school in Toulon. So that was good for me. And so we have, what else? We add harmonic tides at the boundary, and they're adjusted for this mean dynamic topography. Okay, so I could run a movie and we just have, eddies and things, so it looks great. Okay, so it works. No data assimilation in this system yet. We use data assimilation to correct biases in the boundaries, but I'm here going to show some results of the free-running model from one of my grad students, Alex Lopez. And we have all of these observations, though, from Maricus in our IUS database. So this is just 2005 temperature and salinity. We get those data in real time, but this is the archive. But if we want to just do a skill assessment on how well our free-running model operates for 2015, there's also some data we get in delayed mode. And so more data is always better. And the more different it is, the better. And we've got some interesting added sources of data here. The trawl fleet, they have temperature sensors on the doors to the trawls because they're trying to hit certain temperature waters because they know what the fish that they're aiming for like. And so we have data around this entire area from the trawl fleet. And you can see a whole lot of it lined up on the continental shelf edge, which is why we don't ever deploy moorings along the continental shelf edge, and we try never to fly gliders through the continental shelf edge because they get trawled up. So we have those data. Um, there are temperature sensors on lobster traps all through. So if you ever had Maine lobster, there's all of these lobster fishers put temperature instruments on their pots, and here on George's Bank and the South Flank. So now we get this information in delayed mode. Sea surface temperature, not a problem. You've got lots of satellites. Bottom temperature, very limited in terms of data. So we get whatever we can get. Loggerhead turtles have tags on them as well. And so this is all the turtle temperatures that we have. Yeah, incredibly rich set of data. And here just shown as a function of depth. They go all the way down to the bottom, 50, 60 meters on the Mid-Atlantic Bight shelf. This is a range latitude north to south. So, and right up in the estuaries. So incredibly valuable data set. Okay. So if we've got all of those observations here and our added delayed mode ones, we can put those into a skill assessment. And so I'm just going to show you a couple of plots. So everyone's seen Taylor diagrams before. Are you familiar with these? So the way we depict this is the distance, this normalized Taylor diagram. So the radius is the ratio of the standard deviations. So you want that to be 1. So you want to be on the unit arc here. Correlation coefficient is the angle. So ideally you have a correlation coefficient of 1. So a perfect model would fall right on that point there. You can also depict a bias in the model by sticking a little stick here next to this point, and in which case the centered RMS error, which is what you usually plot in a Taylor diagram, squared, plus the bias squared would be the RMS error squared. So that hypotenuse of that right triangle is the total error. So it's unusual to see people do this in Taylor diagrams. Oh, and I'm just going to show you some skill of the control case. A couple of sensitivity tests we did by using different precipitation fields and different boundary conditions. And so this is here a Taylor diagram. The colors of the symbols correspond to different areas through the model domain. And the triangles pointing up are for sea surface temperature, and the ones pointing down are for subsurface temperature. So sea surface temperature we tend to do better consistently, not surprising. Subsurface temperature, not quite as good, but still pretty good. And we've got about the right amount of energy because the standard deviation is correct, but we're not as close as we would like to the perfect point here because there's no data assimilation in this. So, the eddies, the mesoscale eddies are not going to be in the right place. If we did something to get the eddies lining up, we would have a chance to drive ourselves towards this point and get better correlations. Some other things. So, so I'm just pointing here in the case of the orange values. So the control case is the open circle there. The filled case, filled circle, is where we use a satellite-based precipitation instead of the weather forecast model. And it didn't really significantly improve anything, hardly even change anything anywhere. So we left our control cases using the NAM weather forecast precipitation. We also ran a case with taking boundary conditions from global HICOM, making the same bias correction that we did for Mercator. And for some areas, like the outer shelf and the orange square here, that actually degraded the forward free-running model skill. So we stayed with our Mercator boundary solution. A conversation I had with Eric Chassignet a couple of years ago at a GODAE science team meeting emphasized the importance of when you're calculating the wind stress, the ocean surface stress, you should take account of the fact that it's the relative speed of the wind and the current that's going to generate the stress. If the ocean's moving at the exact same speed as the atmosphere, there's no stress, right? So if you modify the bulk formula to take account of that, you see an improvement. The open circles are our control case, and in every region we move closer a little bit, but we improve things. So we've done this sort of skill assessment of our free running model and decided, okay, we're going to make that change to the control case. All right. So we've got these moorings in the Gulf of Maine. So I'll just show a couple of plots here. So this is the squared coherence. So now I want to see how things are matching up in time, even though we're not doing any data assimilation. But if you look at a point in coastal Maine, we've got a significant, if there's a blue line here, it's statistically significant coherence. So we've got some skill across all frequencies in the coastal current, where it's locally forced by buoyancy and winds. If I go out to the northeast channel, the entrance to the Gulf of Maine, we're okay at the really low frequencies, which is just the seasonal cycle, so we've got that right. We're doing well at the high frequencies, the locally driven parts, inertial oscillations and tides and local wind forcing. But in sort of this mesoscale gap here, the two are not consistent, are not coherent. So whatever the larger scale, several day to week variability is, we're not lining up, we're not getting those things. So that again is evidence that, well, maybe this would improve if we go to data assimilation. So we believe we have a skillful forward model. We can see that there may be some added value in assimilating data in the region. We are saying, we're making this leap of faith, I guess, that if we configure this model well, we pay attention to having unbiased boundary conditions. We do the best we can with our meteorological forcing. We get the best estimate of the river inflows. If we have a basically skillful model like ROMS, we should be able to improve upon the global analysis from a GODAE-class model like HICOM or Mercator. Plus, these are the data that went into the Mercator analysis. This is from the Copernicus Cora database. This is all the data that we have available to us in our database. So you see, we can get all kinds of things here through the coastal zone that are not going into the Mercator global analysis. I mean, they don't have a relationship with every observing system around the coast of America, let alone globally. So it's not surprising. They do have some coastal data in the Gulf of Maine, the provenance of which I'm not sure. So when we assimilate even more data than is accessible to Mercator, we also believe we should be able to improve. And so just zooming in on this area, you can see we have gliders operating as a part of Maracus. There are glider trajectories here that are operated, we operate for the New Jersey Environmental Protection Department of Environment because they want to monitor oxygen conditions in case there are hypoxia events. So we have extra data here that is not accessible to CMEPs. Plus, we have everything that we get in real time. So these are our real-time data streams, and I'll talk about these more in the next lecture on Monday. Altimetry and HF radar components, sea surface temperature, any asset that's in situ. A lot of these are, so you can see Argo floats that go to 2,000 meters, some other time series moorings throughout the region. And you can see we're very fond of the NOAA ERDAP service. We are using this increasingly for data ingest and analysis. So the next lecture will be the data assimilation. So we're going to take all of these observations in real time, the initial background estimate from this free-running model that I've described, project the background onto the observation locations. This is the model data misfit here. And then through the magic of 40 var assimilation, we come up with a better estimate of the ocean state. That's our objective. Conclude with just a couple of thoughts. So this is a hurricane glider deployment during Hurricane Hermine in August 2006. This is what the glider saw on its trajectory during from deployment to recovery across the shelf. You can see it's hard to steer in a straight line during a hurricane. This is the analysis straight out of Mercator. And I've had to say, I think this is spectacularly good. This is a global model which they have made no particular effort to exactly represent the Mid-Atlantic Bight Shelf, and yet they've got the surface temperatures right, the bottom temperatures are close. You can see it's a little bit too mixed in that region. But if you looked at one of these GODAE-class models 10 years ago, they wouldn't have had this kind of skill in continental shelf oceans. So hats off to them there. But now we see the advantage of having a regional downscaling. We can get a much better representation of the true glider trajectory. These data were not assimilated in this case. Okay. So we're starting from a good place. We can only get better if we assimilate those observations. And so hurricanes and storms are just another example. So here's our improvement. Just another example of societal impact. This is Hurricane Sandy. This is the construction site for the new World Trade Center. This is what a 4-meter storm surge does. It just poured into the construction site. It poured into the tunnels that go underneath Hudson River that all the trains run in, and it was just a huge disaster. We've had nearly 1/2 a metre, I think, maybe of sea level rise in this region over the last 70 years. And one scientist, Dan Schrag at Harvard, said that by mid-century, the 4-metre storm surge we had from Sandy will, because of the shift in the that probability density function, that will be the new normal on the eastern seaboard. So, societal impacts. And I'll stop there. Thank you. Ninya.
Yeah, microphone, please. I need it. Well, then I give you.
The question was, is the two-way nesting data assimilating? Not yet. That was the Pioneer, NSF Pioneer project that we have, me and Andy Moore at UC Santa Cruz, is specifically to develop that. But of course, being Andy and Hernan Arango doing it, they want to build a Cadillac, Rolls-Royce. I think there is an intermediate step you could take, which is you could use two-way nesting in the background trajectory. So you could just do the data assimilation in the coarse resolution model, and then the final iteration, the final outer loop, when you make your forecast, you can run a different version of the code for that. So you could run the nested code for that, and that would then become the background for the next assimilation cycle. So that would be a way of getting some of the information, the large-scale information, into the nest. What it doesn't do is take very high-resolution observations in your inner nest and appropriately upscale them using the magic of 40 var. Bing, yeah.
I was just wondering if you compare the annual mean of the model SSH with the satellite SSH.
Yeah, and the satellite SSH is terrible.
Okay.
So because when you come into the coastal zone, all that variable bathymetry, you have very short length scales in the geoid, and the other factor is in the altimetry mean sea surface, which is based on a long-term average of range-corrected altimeter data, and in most instances, those range corrections have eliminated the coastal zone for various reasons. And what really needs to be done is we need to do a long-term, I believe, a long-term analysis of coastal corrected altimetry in a consistent way across all emissions, the way we do in producing multi-mission products in altimetry, calculate a new mean sea surface from that. And that mean sea surface from those altimeter tracks is interpolated to a gridded field. That's how we're able to have a mean sea surface to have a multi-mission comparison of satellites that are recently launched, like Sentinel, that does not have an established ground track, or Cryosat. But that mapping process itself is a relatively smooth optimal interpolation. And there are ways that I think that could be done better in the coastal zone.
Thanks. The other side.
Had to take turns side to side so Joaquin gets his work out.
Thank you. I have a question about the ROMS module. As we know, recently, such as the African module and MIT GCM module, they have the non-hydrolytic module. So, because I don't know why ROMS until now have no the non-hydrotic module. Do you have some plan to develop this module? Or why?
So just to clarify, you meaning non-hydrostatic?
Yeah.
Yeah. In the vertical, non-hydrostatic vertical momentum equation.
Yes.
Yeah. Well, that requires a major change to the kernel. I know that there is a prototype version at UCLA that's not open to the community, so we don't have that. But I believe the Croco model, and there's probably people in this room that could speak more knowledgeably about that version, that evolved version of ROMS that I think has taken non-hydrostatic core out of the Symphony model, or is it? Does anyone know? Yeah. So Eric Chasigny might be able to answer that. That's not the development path that we have pursued. Those are not the physics problems we're interested in. So for us, hydrostatic approximation is good, and we're working on coupling to atmosphere and waves. We're working on data assimilation with the variational methods, and we would need to have an adjoint and tangent linear model of a modified non-hydrostatic kernel. And I can't even bear to think about doing that.
Thank you.
Okay, that's all.
Okay.
I want to make a comment, John, very quickly. I think you have all had the pleasure of really listening to something which I think is very, very important today, and I want to say that and to have your comment, maybe, John. And that is, before really doing any data simulation, what John has just shown is that you need to be sure that your model is able to reproduce the main physics and the main really observations that we have. John was putting from his initial slides ocean state, and he was just showing us the main features in the area. That's without data simulation. And this is a must of any model before doing any data simulation. Otherwise, you might be ending up getting the good results for the wrong reason. And I think this is very, very important. Any comment?
No, thank you. That's a very good point that I should have made myself. Data assimilation will not fix a bad model. And the fundamental underlying assumption is that your observations and model are unbiased. It starts from that. No one knows how to do assimilation of biased data. So this is why we go to all that trouble to get all the biases out of our boundary conditions so that our forward model has a chance of, at least on average, looking like the climatology. And data assimilation, you hope, will just make things better from there. But thank you, Joaquin. It's a good point.
Thanks a lot, John.